Welcome to the DD1324 online lectures. In this lesson, we will cover dynamic memory. When you run a C program on your computer, it uses two types of memory from the operating system, static and dynamic. The static memory is a fixed size determined by the compiler. It consists of the code, which includes the source code and the instructions that need to be executed, static and global variables, as well as the stack, which is used to store function calls and local variables. Everything has to be stored in the static memory must have a known size when you compile. If, for example, you don't know the size of an array until the program runs, you cannot keep it in the stack. It has to be kept in the dynamic memory. The dynamic memory, also called the heap, can change in size. You, as the author of the program, control how much memory you want to use from the heap and for how long you want to use it. The heap can grow as long as the computer does not run out of memory. When you use the heap, this is called dynamic memory allocation. Let's look at an example of a simple program where we keep all of our variables and memory on the stack and we do not use any dynamic memory. In this way, we can see the advantages of using the dynamic memory in a later example. So, in this bit of code, we have a simple program that takes two numbers, a and b, and then computes the square of the sum of those numbers. When the program begins, the main function is invoked and some memory on the stack is allocated for the execution of main here. And it also allocates some memory for the local variables a and b. Also note that within the static memory we have the source code residing in this part of the memory, and we also have total, which is a global variable that was declared at the beginning of the function, which is also stored in the static memory. When we begin to run the main function, the first thing we do is we declare and give values to the integers a and b, 4 and 8, and then we arrive at the square of sum, the call of the function square of sum. At this point, the main function pauses, and then we push square of sum onto the stack. So we make a new stack frame for this function, which has now integers x and y, as well as an integer z as local variables. At any time during execution of the program, the function at the top of the stack is always the one executing. Here now, we've proceeded into square of sum and we've encountered the function square. So the square of sum function is paused, and now we've moved up to the function square, which passed the variable 12 as the input integer x, and square will return 12 times 12, or 144. When the function square has finished running, it's popped off the stack and control is now given back to square of sums. Square of sums then stores the value in z to the global variable total, and then square of sums is popped off the stack, which returns control now to main. Next, main moves to the next statement, which is a printf, which prints the total, the global variable, and this pops the printf function onto the stack, and it prints out the total output of 144. After the printf statement is finished, the main function will finish, ending the execution of the program, and everything is cleared from the memory, the stack, the code, and all the globals, and all the memory is returned to the operating system. The important thing to remember about the static memory is that it's of a fixed size. So that means that the amount of space allocated for your code, for the global variables, and for the stack are all fixed and determined at the compile time. If the stack grows beyond the memory size that's reserved for the stack, then the program will crash. This is called a stack overflow. For example, one common cause for stack overflow is if you write a bad recursion and your program makes infinite function calls and it exceeds the size of the stack. This will cause your program to crash. So let's review. Variables on the stack have the following limitations. The local variables inside of the stack only exist during a function's execution on the stack. So as soon as the function disappears, the local variable also disappears. The size of the variable on the stack also must be known at compile time. So if, for example, you don't know the size of an array until the program is run, it cannot be run in the stack. Last, the stack has a fixed size of memory. The heap, or dynamic memory, has a lot of advantages, but also some disadvantages. It's a very large pool of free memory, and it can grow as long as the system has memory. You can decide when and where to allocate and deallocate memory in the heap. In C, you can access memory from the heap using 4 different functions. You have malloc, which creates space in memory, calloc, which allocates space in memory and initializes it to 0, realloc, which modifies the size of memory allocated by the previous 2 functions, and free, which gives the memory back to the operating system. An important point is that the only way to use memory on the heap is through reference by using pointers. It's the programmer's responsibility to free any memory on the heap they requested and give it back to the system. Now let's look at malloc, the most commonly used function for memory allocation in C. Malloc looks for free memory in the operating system, books it for you, and returns a pointer. The contents of the memory can be anything, it's up to your choosing. The basic syntax for using malloc is you give it the size of the memory that you want in bytes, and also give that of the type size t, and malloc will return to you a pointer to the memory of a void type pointer. Let's look quickly at an example where we'd like to make an array of 5 integer elements, and we want to use malloc to create this array, or to build a pointer to that array. So if we were to do that, we could say that n is 5, so 5 elements, and then we multiply that by size of int, so an integer is 4 bytes, so when we call malloc, we'll be asking for 20 bytes, and malloc will allocate 20 bytes inside the heap. It will return to us a pointer, which will be the integer pointer p, and the integer pointer p will reside on the stack, and it will point to a location in the heap, which will be the memory that was allocated to us by malloc. Calloc functions in the same way as malloc, except in addition to allocating the memory, it also initializes the memory so that it all contains zeros. So here you can see the pointer at 208 the pointer pointing to 208 is pointing to memory that has all been initialized to 0. Realloc is a function we can use to resize memory that has already been allocated by the operating system. Here we have an example where we use realloc to resize the array we had previously assigned using malloc and calloc. So in the previous example, we had asked for an array with 5 elements, and now we want to resize it to be an array with 3 elements. In order to call realloc, we give it the pointer to the previous allocation and then the desired size of the new memory allocation. So here it's m is equal to 3 elements times the size of an integer of 4 bytes, and that will give us a desired size of 12 bytes. Previously we had asked for 20 bytes from the operating system, so we'll receive 8 bytes back, or the operating system will be given 8 bytes back, and our new pointer will be pointing towards the same location, 208, but only using 12 bytes of memory. It can happen that if you request a larger block of memory than the existing block, that the pointer may need to point to an entirely new location because there is not enough free contiguous memory after the existing block. After you've finished using a block of memory, it's important that you give it back to the operating system. If you don't, you can create memory leaks. To free the memory, you use the free function. The free function is a very simple function where you just need to give it the pointer to the memory that you want to give back to the operating system, and the function will give the memory back. It's also good practice afterwards to set the pointer to null so that it cannot be misused. By calling free like this, we return these 12 bytes that we had requested using realloc back to the operating system, and we set the pointer to null. Now let's look at an example of a simple program that uses malloc to create some dynamic memory in which we're going to store an array. The important thing about this example is that the size of the array is not known before we run the program. You can see here that in main that we're asking the user to type in array size, and then we use this to decide the size of the array that we keep in the memory. So here the user has said that we would like an array size of 5. So in this line of code, we create a block of memory in the heap using malloc. So n is the size of the array that we requested from the user, and we multiply that by the size of an integer because we want to create an integer array. And this creates a block of 20 bytes in the heap. And we assign the pointer returned by malloc to the pointer p, which we declared here. So now inside of our stack frame, we have the main function with the pointer p, which is pointing to block to memory location 208, and we also have the variable for the size of the integer array. Now in the next step, you can see that we have a display function here. We haven't filled the array yet, so if we display whatever in the heap, most likely it will be filled with zeros, but it can be filled with almost anything because when we allocated this memory with malloc, we didn't format the memory to 0. So when we call this print function, the output could be some, very strange integer values. Next, we call the fill array function. This fill array function takes the pointer to the array, and it fills the values of the array one by one sequentially. So after that, we call the display function again, and the output is 1, 2, 3, 4, 5. After the display function is finished executing, we'll return to the main function. Here we call free, and this frees the memory, so you can see here this memory from the heap has been returned back to the operating system, but it's still filled with the contents that we had filled it with before. Then we assign the pointer to null, and then we return 0 and we exit the program, which pops main off of the stack and eliminates any global variables or code from the operating system and returns all the memory back. This concludes our lesson on dynamic memory. Thank you for watching.